Alrighty, hey everyone. I'm gonna try to cover chapter 9 and 10 today. And we're gonna start with a bullet fired into a wood block. And this is, I believe, momentum. Yeah. So we're going to use this equation. The P is equal to mv. Right? Note here that it says inelastic collision. Or it doesn't say it, but it's inelastic because it's going to be deformed. So this block here is going to probably rise up from the ground and have the bullet embedded in it. So this embedded tells you that it's inelastic. Go ahead and draw. All right, and then the bullet's right here because it like broke through the wood and now it's there. And then you have a new V and then new M. Where the new mass of the block is M of bullet plus M of wood. This is M wood here. And bullet tells us it's 24 grams. Right, and then if we do our King Henry, so we can move the grams over to kilograms with 3 hops. So that becomes 0.123024 grams. 4 kilograms, sorry. Okay. You can also note that the V of the wood here is 0. Because it's at rest, right? So at rest tells you that V is equal to 0. And then this is our V of the bullet. Cool. So then from there, we can state that P show equals P final. Okay. And then we can state that because we know this is an inelastic collision. And for inelastic, only the momentum is conserved. So you know something's inelastic because maybe they hit, but then the masses stay together, versus an elastic collision where they're going to hit and then bounce off each other. So if it says embedded, sticks together, then it's inelastic. But for either one, you can do momentum is conserved, which is what this P initial is equal to P final means. So then, what do we have in our initial side, right? We have the mass of the wood times V of the wood plus the mass of the block plus V of the block. And I'll write in the thing right now. And then it's going to equal to new mass. I'll do this as big M. No, I'll keep it little m. Can't edit this, can I? No, I can't. You can just draw it over. I'm gonna make this big M, just so we can distinguish it. V, and that's the big V too. Alrighty. Let me fit some of this in. Wood, block, block. Right. Now notice that V of wood is equal to 0. So this is equal to 0, right? Because something times 0 is going to be 0. So then that gives you mass of the block times V of the wood is equal to total mass and final V, right? So then from there, you just simplify. What are we solving for? We're solving for how high the block will rise. How do you need to figure that out? You need the velocity to figure that out, right? So then that's equal to 0, and we can divide both of these by big M. So then that gives you, change colors here. Big V is equal to MBVB thus total mass, final mass. Okay. Now you can leave that just as is, or you can just plug in and solve for it. After it becomes embedded, that's your new V. And then from there, it's just your kinematics equations, your Y final is equal to Y initial plus V time. Wait, no, we're probably gonna use a different one, huh? It'll probably be V initial squared to I'll leave space for it. V naught squared plus 2A. Oh, no. We're not doing any of that. Oh my gosh. We're using V is equal to delta T over DT, I think. Oh, never mind. This is like I was trying to make this simple. This is like when we would throw something up, so then you would solve, I was right, the Y is equal to Y naught plus V naught T plus 1 over 2. In this case, it's going to still be gravity since heading upward, T squared. Where you're solving for T, and Y naught is equal to 0. Then plug in. No, because then you still need the final one. You're going to plug it into this one. And you're going to use V is equal to V naught plus AT. And A is equal to graph. This won't actually be part of the problem. I doubt she'll include anything like this because we ever covered those chapters and she doesn't want to test you on that again. This is just the problem that it states. But the main thing I wanted us to do with this one is find the V. So then let's plug it in here. Wrong one. Okay, so this how high you would solve by this, but you don't have to. You don't have to worry about it in this case. Then this one came over here to become that. We're gonna go ahead and plug it in. Because we have all of this stuff, right? So you have MB, mass of the bullet, which was 0.0024 kilograms. Remember, you wanted in kilograms because we're dealing in newtons and SI units. And then it's going 310 meters per second. And then the total mass at the end is the bullet plus the mass of the wood. So 1 point. You solve for that, it should equal to what did I get? I still need to plug it in. 0.024 minus 310. 5.2 meters per second. Right, because the kilograms are going to cancel out. Cool. Let me go ahead and take a screenshot of this. Right, next one. So this one you have a nail. And you've got a hammer, which I'm just gonna do a block like this. I'm not trying to draw. That's a hammer. And then it's gonna strike the nail at a certain velocity. So we're gonna do this again. But this time it's asking for what's the average force in the impulse, right? So impulse is defined as J, which equals I can't do the integral sign, but F dt should be able to get, right? That also means that F is equal to dp over dt, which becomes F dt equals to dp. That means that impulse also equals to the integral of dp. Unless we have like a force equation, or sorry, equation with like symbols for p, then that just means that the integral is going to be p evaluated at the initial and final, which we also know as delta p. Okay. Which is delta p is the initial minus the final. P final minus P initial, which is the same as M1 V1 minus M naught V naught. You don't normally write the one, so. So this is the initial up here. And then after it strikes it, because we're gonna need to imagine this. The nail will probably have gone into the wood a little bit. And so then any energy that was input into the nail doesn't turn out into like kinetic energy or potential, it's deformation. So it's negligible. And at this point, right, the hammer, oh, that's a bad hammer. The hammer has hit it. And I'm being lazy with my hammer, so it's just a box. Try it. There we go. Hammer has hit it. This is the initial position, and this is the final. So in the initial, we have the hammer, I'll leave space, is equal to 8.5 meters per second, while V of nail is equal to 0 meters per second. Right? That's kind of why we can make this negligible, because in both cases, the nail is 0 meters per second. Also, when we're doing delta P, we're only looking at the hammer. So I guess that's something important to mention. I'll leave this as a little V. And then at the second one, it's at rest, so it's 0 meters per second. And let me include that all in referencing, all in view of the hammer. And then the view of the nail is 0, but both times, so that's an extra reason why we do only by the view of the hammer. Cool. So then this is your V naught. Because V of 0, sorry, V final is equal to 0. That means this is equal to 0. Right? So then we can go J, oh, not red. J is equal to P initial, right, negative P initial, which is equal to negative M not V not, I'll write those in. And then we can just plug that in straight as is. It's negative M is 12 kilograms. Because it says in the equation, or sorry, in the problem. And then 8.5 meters per second. Which should come out to be negative 1.02 newtons times seconds. Okay. Note that negative makes sense because this impulse is stopping the velocity. Which does stop momentum. If it's positive, that means you're increasing momentum, which is key. Okay, so that's the first question. Then the second question asks, what is the average force acting on the nail? We remember that J is equal to dt, sorry. And you also know that this could also be J is equal to Ft, right? Because the force is average. If you're assuming it's average, then you're not going to have like an equation for force that's going to make a change. Probably should have written that in a different color, but oh well. So J is equal to force T. So then you're going to go ahead and divide J by T to get force. And then your force average, we're going to go ahead and plug it in. Because we calculated J already. -102 seconds. And then you're going to divide by, I think it tells you the amount of seconds. It says 8 milliseconds, which should be 0.0. Zero 08, I think. So negative 102 divided by 0.008 is negative 12750. Oh. 12750 newtons. Right, and then again, it's going to be negative because it's opposing the origin of motion, where you had a positive, prime. You had plus v here, right? So then that means anything coming this way is going to be negative. Because it's opposing the motion, because by saying this is your plus v, then you're saying then this is your positive axis and this is your negative. This looks like a weird schematic case. Cool. And then that solves this problem. Let me just make a few notes on this little stuff. This is newtons per meter squared because it results in kilograms. Kilograms, meters over seconds. which is the same as newtons over, because newtons is kilograms, meters over second squared, right? So then if you multiply that by a second, then that gives you that unit, right? Because that second's going to cancel out. So you have the squared here, and that cancels that one out, and that gives you the units that you see there. I think, was that all I wanted? Oh, right. Here you have the 10 milliseconds. Milli, so 1, 2, 3. And then that gives you, I'm just showing you where I got some stuff. Maybe do this in different color, yeah. 0.00. Eight seconds. Alrighty. Next one. I'm just gonna plug in my laptop. It's coming. There we go. So this is another impulse one. I felt this one was important just because it shows you some of the math. You can try and work it out, and I'll try and do it the next round. But seeing as we already did like a kind of collision with, I did this one on the 11/3 supplemental, and then it was also on your practice paper from Dr. C. Same thing with this one. It was also 11-7 practice supplemental, and you got it on, oh wait, no. Sorry, you got it on the practice problem from Dr. C, and it was probably on the 10-27 supplemental. The point is, I think we're gonna skip this one for now. And if I need problems to do later, then we'll go back to it. Right. So this is chapter 10. These are rotation, inertia, and torque, which you're probably gonna use at some point. I wanted to make a quick note that even though like the angular stuff looks scary, you're kind of just trading like different values for them. So this is just a little up in this corner. Here we go. I'm in this corner. There's just a few equations that I used to use a lot. And then here's just how you relate linear to angular velocity and the displacement stuff. So x turns into theta, v turns into omega, and a turns into alpha. Cool. So say for your velocity equation, you have x over t, which becomes theta over t, because you have the x turn into t. Same thing with the velocity. For the acceleration equation, the v turns into omega. And then you get your x, or your angular x, from this. Like, as you're going around the circle, how far do you go in terms of the radius and your start point? You probably won't do this at all, because finding this curve here is a pain. But I just wanted you to know where you get it from, because it helped me. Because it's just the theta here. All right, she also wanted me to go over torque. These are some notes from when we did torque in class. Note, you always need a lever arm, and you always need the thing to be perpendicular to the force. So, and then the longer of a lever you have, the less force is needed, and the force cannot be parallel to the rotation axis. So see this here, this should have no torque, because you're pushing directly into the axis, and it's not going to rotate at all. Same thing with here. If you were to like pull down straight from here, then no torque. Oh, I probably just didn't know. But then say for here, you have your torque from here because you have your components, right? This is always a little tricky because it's like right here is the Y component. So this one has no torque. But the X component does have torque because it's perpendicular to the axis. And then in a case like this, your torque is coming, this distance right here between wherever your force is pulling from to the axis of rotation is your length or your lever arm. So so for here it's the radius, and also here is the radius of the little circle. It's supposed to be an L. So I'm just saying that the radius of the circle can be your lever arm if you're pulling outside of like the center of the circle. So now we're gonna do a torque problem. You have a bolt here, and you got it's asking you for the force on two different spots. It says the torque that you need. So you need a minimum of 75 torque. And then it tells you the length, which is already drawn. This millimeters is the diameter. So let me type that. So you need to turn that into radius. So diameter over 2, because half of it is equal to R. So then we're going to turn this 55 millimeters. Sorry, 15 millimeters. Into milli, so 1, 2, 3 on the King Henry. 0.123 spaces, meters. Divide by 2. The radius will be length from so then that's why you need to divide by 2. 0.015 divided by 2. 0.000, I think. Yeah. 75 meters. We'll use that later. Now let's go back. So you're given torque and you're given length. Notice that both are perpendicular. So 90 degrees. So then that means that torque is equal to just force times length. Where like this is the length on the wrench. And then this is for the length of the bolt. I guess it would be useful to mention torque is a cross product, which means that you're crossing usually two vectors or I guess in this case it's one vector and a scalar, and you result in a vector. And the way you usually do cross products, if it's not like a long equation, is you do FL sine theta. That's my theta sign. So then in this case, if perpendicular, okay, theta equals 90 degrees. FL sine of 90 is equal to FL, because sine 90 is equal to 1. Cool. So that's why I'm saying that we can just use torque is equal to FL. Anyway, from there, you're probably going to divide both sides by L, right? Because you have L. But you're solving for torque. So that gives you force equal to torque over L. And then we're going to do this twice. One for the wrench, one for the bolt. So let's draw a line here. So that means, let me see how much I can take. Wrench. Then bolt. Force on wrench is equal to total torque needed over the length of the wrench. And we'll plug that in soon. Similarly, the force of the bolt is total torque needed. That doesn't change over the length of the bolt, which does change. Let's go ahead and plug in these numbers. Oh, that was way too long. Total torque is as given, 75 meters times newtons. And then the length of the wrench is, oh, I didn't convert it, 28 centimeters, which is 0.28 meters. I'll convert it right now. Then the length of the bolt, which we found to be 0.00075 meters. You do want it in meters because you want it to cancel out. No, not that one. Draw. Meters, right? Because you have millimeters. Sorry, you have centimeters. So that's centi, 2 hops, whereas a milli was 3 hops. And then you plug those in. You just draw this first. $75 divided by 0.28. That equals 267.9-ish newtons. And then 75 divided by 0.00075 is 10. No, wait, more. 1000000. And the point of this is to show you how much that distance the lever arm matters, right? Because I don't think anyone can do like 10,000 newtons with your like fingers when you're trying to turn a bolt, but adding that extra lever arm to turn the bolt decreases the amount of force that you need at the end of the wrench. So the further down the wrench you grab, the less force you're going to need, and the easier the job is. That was the point of that one. And then we go ahead and take a screenshot. Oh, we still have a few minutes. Next one is determining inertia of a door. Let's draw this door. You have the door on a hinge, which is going to be axis of rotation. So let me make the hinge a different color. I'll type it later. Then you have the door, which is 0.5 meters high. Oh my gosh. Point. And 1 meter long. Note that this hinge, simple, hinge equals axis rotation. Cool. And then you're going to thickness. So first off, we need to find the moment of inertia equation, right? So you're gonna have, oh, I had moved it. You're gonna have a diagram or a chart like this, right? It's not a hoop, it's not a cylinder, it's not a sphere, but it doesn't give you a rectangle, right? So if she gives you this specific one, I'd probably use the long uniform rod, right? Because it's kind of like the same thing. You're just missing the width. But if you look it up, this wood plank is also the 1/3, the same as the slender rod, because you're not focusing on how long it is in terms of like how far along the axis it travels. You just focus on how far the end is from the axis of rotation. So we're going to use the 1/3 MA squared. So let's draw. A is equal to 1/3 and A squared. Where they say A, but this is A. It's not acceleration. And if you don't believe me, we go back to look at the image. You see how it says A, and then it points A out right there. So let me So it says this is A. This is A. So this length from how far it is along the axis is A. And then mass, M is usually just mass. Every time that I've done this, it's mass. I don't know why they did a big M. I think they just wanted to. Now we plug in 1/3. I should probably say I'm plugging it in. Mass, 19 kilograms times A squared, 1 meter squared, which should equal to 6.3 kilograms meter squared. I'll write in the squared right now. Right, and I just got this for mass. And wide is how far it is from the axis of rotation. That's where we got it. And then that's your answer. And you're done. Cool. This is kind of a similar one. I think I kind of want to start on some chapter 11 stuff. I'll do that one. This is just going to take a little bit longer. And that way we're done with chapter 10 and 11, 9 and 10, sorry. Alrighty, so you've got a bowling ball. It's not on an incline, but it is rolling. So let me draw this. And it's rotated, right? Because that's what it means by rolling. Okay, go snap. Oh, it's not circle. Such a good circle. I just realized I can do shapes on here. Anyway, it's rotating, right? And it's also moving. So you have translational energy and kinetic energy. Sorry, and rotational. And both of them are kinetic energy because it's energy of motion. And all that means is that you have one that's turning and one that's moving forward. Right, so if you're just standing in place, turning with like no direction, that would just be rotational energy. Versus if you're also just sliding without rotating at all, then that's just kinetic translational energy. Let's deal with some units. Just this 9 centimeters has to become into meters. So centimeters to meters is 0.2 moves, so 0.009 meters. And that's this radius here. So that's what you're going to use for your inertia, right? Or moment of inertia. So there's actually an equation that relates translational and kinetic energy. It's K total equals 1. You just add them basically. Add 1/2 and V squared plus 1 over 2 I omega. I'm just going to use W because I don't have an omega. I'll write it. Squared. Cool. So you can do this two ways. You can plug it in. Oh, wait. I'm skipping ahead. We need to find the I equation. Sorry. So you're right. This is probably an uniform sphere with the radius or center of rotation through the center, right? Because you're going to have the center and then the ball is rotating around it. It just happens to also be moving. Right? You have, this is the center of rotation, and you've got the ball just kind of rotating around it. So like, but it also just happens to be hitting the ground. So whenever it rotates, it also kind of, in terms of the ball, the ground is moving, but the ground doesn't actually move. So the ball is just kind of going like this, right? But it's not sliding, so there's no force friction. It's just rotating. Oh, okay. There is force friction. That's what causes the ball to move. But it's not like there's work being done by force friction is what I meant. Okay. Anyway, so we're gonna use this I, the 2.5. 1. Let's see if I can just type in. It looks like it'll pop this thing. I equals 2 over 5 mr squared. And the r squared, not everything is squared. Right, and we're getting that from this one. Cool. And then also note that from earlier, oh, I need to get out of the notation. Earlier, oh, Germany. All right, well, there's an equation back here that says that B is equal to, let me see if I can move something. Yeah, here. This one, V is equal to R omega. So, if V is equal to R, R omega, then you're gonna go ahead and divide by R to isolate omega, right? Where R is radius. Which we also use as little r. So it's the same thing. Skipping ahead. Omega, I'll use space for it, is equal to V over R. V over. And that's just how you write the symbols, kind of. All right, let me move some stuff back. It's here. I was gonna write omega there. wanted this over here. Cool. So you can either do one of two things. You can, let me type this. And solve for I and omega separately. Or you can plug it in with symbols. Simplify it and solve. Personally, I prefer symbols, so that's what I'm going to do. But I just want to let you know you can solve them separately. So we're going to take this I, put it in here. We're going to take this omega, and plug it in here. So then that gets you goes to 1 over 2 and b to the power of 2 plus, I'm going to write this out because it's going to be a bit. I should also. So we had the 1 over 2 that was already there. And now we have the 2 over 5 from the I. And then the mr squared from the I. And then you have the omega. You have the omega value, which is v over r. And all of that is squared. Cool. Note that this is 2 over 2, so that's going to cancel out. When you input the 2 over, it's going to be v squared and r squared, which means you can cancel these two r's out. Cool. That gives you the equation. Wrong color. Total 1 over 2 m v squared plus, it would now be 1 over 5 m v squared. And here, because you have the same m and v, you can factor them out to give you k is equal to m v squared, all of that, times, let me just write it, because all the parentheses are going to be confusing, I can tell already. mv squared times over 2 plus 1 over 5. And because you're going to use a calculator, you don't have to simplify any further with fractions. Oh shoot, that's totally the wrong color. My bad. I don't feel like rewriting it. Let me see if I can change the color like this. Cannot. Alrighty. That's staying like that. Plug it in and get okay to m, which is 77.3 kilograms times v squared 3.7 meters over seconds. That's going to be squared, so leave some space for it. Times 1 over 2 plus 1 over 5. Should get you k is equal to 7.3 times 3.7 squared times 1 over 2 plus okay. And that gave me 69.96. Oh shoot, what did I do? Newtons meters. So that's about 70 joules. Right, joules is work or energy. I'm pretty sure. There should probably be more parentheses here. Just so your calculator knows that it's different. So this is squared. Oh, and there's your answer. Screenshot. Alrighties. And that's it from me for today. Hope you have a nice day.